from in 전라북도.
Okay, how about you? Seoul? Okay, that's boring. How about you? Incheon? How about you? Patong. Okay, how about you? Oh, that's boring. Sorry. Okay.
인천.
Incheon.
대구.
Daegu? Okay, how about you?
Here.
Here? But I was asking him first. Okay, you're here. Yes.
불러야
Okay, you're from here originally. Okay. How about you?
전북 구미.
Oh, okay, that's close. My how about you?
경기도 여주.
So you have to scan around immediately sometime soon, right? Are you traveling to, or you're not there to visit your parents? Okay, anyway, so when I was a student, let's see, I don't think we. If I say probably, that sounds like I'm very old, but I'm not. Probably I am. But when I was a student, okay, I was studying. So during the this Thanksgiving holidays or whatever New Year's, I had to go to not quite Daegu, but small little town close, not even close to Daegu. So we had to take the train, but then there was crazy this thing that you cannot even buy ticket, right? So you have to just stand. But back then, fastest one was the Temar, Temar, right? We didn't have KTX or SRT. That's the fastest one, but too fancy for me. I mean, I'm a student, I'm a poor student, I cannot afford that. So I had to go with the Bunghwa. That was still decent option, but it takes like 5 hours. I'm standing, and then it's not like you stand with the room. You literally stand like that because it's packed of student people. So I picked my favorite book because it's so boring, so tough, and challenging to go through. Start reading it, but at some point my feet like, what are you doing to me, right? So painful because you have to just vertically stand without even moving like 5 hours. And I remember that. So that was not that funny period for me, but hopefully these days is better. Is it very hard to buy a ticket during the holiday these days? Oh, okay. Hopefully you, not two of you. Hopefully you already bought tickets to be able to go. Okay, let's go. Let's move on. So let's move on to the discussion of symmetry. Okay, so let's talk about symmetry. If I have a white book, if not, that's the end of today's class. In fact, that's the end of today's class. Enjoy your. It's okay. It's okay. Nothing's gonna happen, right? So okay, so we talked about symmetry. So the key thing is symmetry. Symmetries and conservation. And today the goal is to first lay out the language and then we hopefully finish all of the space-time. And then next we're gonna cover the internal symmetries that we will develop for today. That's the goal. So last time I already introduced you basic notion. There's this theorem called Noether theorem. So first I will derive the general statement about this, and then I will focus on particular class of symmetry and symmetries, and then we will derive, I haven't even finished the conservation. Okay. So symmetry, as you will see, is one of the good reasons we use a Lagrangian formulation of the quantum field theory. In fact, even beyond that, back in 1950-60, there were two separate programs in the fundamental theoretical physics. One was about understanding and developing consistent quantum field theory. The other was what's known as scattering amplitude. Okay, so the other direction, known as scattering amplitude, the goal was, if I'm given this initial state and then this final state, okay, can we just mathematically demand consistent conditions to determine this analytic function that should control that? Can we just do that? Okay, so it's sort of an idea of bootstrapping the final and ultimate answer, basically by just demanding all sorts of mathematical rigor, okay, and consistent conditions. At the beginning, that was very successful. Because quantum field theory, a lot of times, is about the perturbation theory. So you start with the classical action, you quantize a little bit, you turn a small perturbation and start studying. But in nature, the first sort of interactions or scattering properties that human beings have encountering was strong dynamics, like hadrons. Okay, so perturbation theory, okay, it looked very hopeless to use it. So F-metrics program, therefore, was very popular, even on West Coast side, like Berkeley, that side. If you are quantum field theorists, you're screwed up. Okay, there is all S-metrics, and Weinberg went to the Berkeley. I think as a postdoc, he was still like quantum field theorist, but like people surrounding him was like, "What are you doing here?" Right? We're all S-metrics. But then, eventually, I mean, from the modern perspective, we learned that symmetry is one of the most powerful tools in understanding or formulating fundamental physics. But asymmetries is very hard to incorporate the notion of symmetries, at least back then. But Lagrangian is very easy to start. Okay, so that's another reason why that's very important. Anyway, let's not wait. Closure theorem. So what's the statement? Let's consider an action of some field. For now, we consider scalar field, but eventually it doesn't have to be scalar field. We can consider any sort of field. Okay, but at least in this class, I assume that there is this Lagrangian formulation of theory. So that's why it matters. And symmetry means that we consider under a continuous symmetry transformation. So far, under the continuous transformation of the sort that phi of A goes to phi A prime X, say some transformation parameter epsilon, and then we look like original field, and then some small deviation from original field, which depends on epsilon. In fact, because we talked about the continuous symmetry, that means that I can take as small symmetry transformation as possible, that is continuous. So here there is a notion of infinitesimal transformation. Okay, so that's why here I'm taking very small transformation, and in fact, this can be approximated as a proportional to epsilon only, and then I can write some symbol that just tells me that this is how field transform. Does this notation make sense so far? Okay, I consider small variation of the field variable, which is this is the transformation parameter. But since I'm looking at the small variation, I can zoom in, or I can look at the transformation, which is only first order in epsilon. I'm just writing my order, and I'm just writing the rest in this notation.
So is there any reason why you want to give it so largely?
Not really.
Okay.
Since Coleman used it, I decided to use it. You can use S if you want. That's also fine. Okay. Well, at least the meaning of notation is clear so far. Okay. So then symmetry means that action shouldn't vary. So when this goes to that, and in the case of infinitesimal transformation, that you asked it because they look like covariant derivatives. Okay. The symmetry means that this shouldn't change. Like that. So that's the statement about the symmetry. So let's just work this out. So first of all, how does action vary? So variation of action under that transformation looks like d for x variation of the Lagrangian. But now how does the Lagrangian vary under infinitesimal transformation? Well, this has two arguments. So one is the phi, the other is the derivative phi. So first I take partial derivative of that with respect to phi of x, and then the way it transforms. Second, I take the derivative with respect to derivative of x, and then how that thing transforms. Now, so what is this? So this is equal to difference of the derivative of phi between transformed field versus untransformed field. Therefore, this is the same as the first one cancels, the same as the derivative of derivation of the field. Like this. Right? That is the definition. So here's the one derivative, and there are two terms. I can do the integration by part, but I'm gonna do it explicitly without dropping any surface looking term. So let's do it, right? So here I'm doing the integration by part. If I do that, I get the following expression. So first, I should get the first term. And then the second, I will get the term that with integration by part dot on it, this, with a common change of field. And then I have to have another term. So this is still part of this integration, which is derivative of okay, so that's the exact answer, right? Without making any approximation. Now I'm going to make a statement here, because naively you might think, oh, that is exactly the same step as we did to derive equation of motion. Almost, yes, but not quite. So let me point it out. So I mean, in the case of it, so yeah, mathematically so far is the same step. But the thing that you want to make sure is that here I'm not taking arbitrary variation as an equation of motion. I'm making a symmetry transformation on it. That's the first thing you have to keep in mind. Okay. Second, therefore, in the case of equations of motion, we said that, well, this is the surface term. I'm going to make sure that either variation vanishes at time to infinity or minus infinity, or field dies off at spatial flight. So I'm just going to drop it. So we got the equations of motion. Right, so therefore you pick a particular class of arbitrary variation which dies off at infinity, basically. Here I'm just saying that take any field configuration which may or may not satisfy classical equations of motion. I'm just gonna take any field configuration. I'm making a well-defined field transformation. Now, this transformation may not end up giving you a zero at infinity. I'm just taking a field variable, taking the transformation right here, right? So this is not necessarily and generically would vanish at the space of infinity. Is that clear? The two important distinction here. Okay. So because of that, now, so far the expressions are exactly the same, but I'm telling you there are two distinctions that you will keep in mind when you look at this expression. Now, what should this be the same? Well, again, the definition of being symmetry for a theory with action description is that this should be the same. So now let's work this out first, and then I'm just gonna equate that. So the fact that action, oh, can you see the blue from the back, or it's worse? That's probably worse than okay. Okay, let me try, but let me know if this doesn't work very well. So this can be achieved because action, remember, takes this form. So this can be achieved so long as variation of action takes generally some total divergence of the field, or possibly the ripple. Remember, here I'm not looking at the symmetry transformed field, which I cannot say that will be dying at infinity. I'm saying there is a function which is a function of a field and its derivative. That I know should die off at infinity because of the finiteness fashion. Okay? So that's the difference. Okay, difference is that may not die at infinity. A field will die at infinity. Right? Because otherwise action on this one is not even finite quantity. Because you're integrating over entire space and time. So, but therefore, in this case, I see that now the question is this same as to say that action is zero? Sorry, variation of action is zero, therefore, this action is same as that? Well, under some circumstances. So let's first understand when this is equal to zero. So that is equal to zero for roughly speaking under the following equation. So suppose I call the space-time manifold to be M sub 4. Okay, this is 4-dimensional space and time. This is true. This is true if F mu at space-time boundary. So when I write this notation, this means the boundary of the manifold M4, so space and time. And that is it. There are two ways of satisfying this condition, or a mixture of the two. Either saying I don't have a boundary. Okay, so for instance, if your space-time manifold is S4, for instance, that doesn't have a boundary. So obviously, if you just look at the boundary value, nothing appears there. It's zero automatically. Two, suppose your space-time does have a boundary, but you can impose the field condition in such a way that this function nevertheless idle. Okay, you can check. So anyway, for those, so either this can be either a space-time boundary doesn't exist at all. This is null function. This is not field. This is null function. This is zero. Say example to be, and for space-time manifold is something like S. Okay, something like that. Or just that or space-time manifold does have a boundary, but still F itself vanishes for some reason. In most of perhaps the entire part of this course, we're just going to consider this situation because we're going to just take the space-time manifold is actually R4, right? This Minkowski space and time, but that is almost the same as S4. Almost. So therefore, we're going to focus on this, and don't worry about the subtlety coming from the fact that there might be boundary, although theory exists with these features. Okay, so then let's go back and ask. So under the symmetry transformation, I just derived the general expression for this. And then the fact that it is actually a symmetry transformation means that this, I want it to be the same as total divergence of some function, which is a function of fields and its derivative. Okay, so far, I just have done general analysis. Okay, now let's derive our golden equation. So what that tells me is that that should equal to that. So therefore, for a field configuration 5, that solves classical equation motion, meaning this term dies. So what I'm doing is, remember, this expression is like, let's look at the point x in every space-time point, right? And then I want that to be, if I just move that term on the other side, there is an integrand integrated over entire space and time point. I want that to be zero, identically. Right? So that means that the integrand should die. And I'm saying I'm looking at the field configuration in the vertical space and time that satisfies the equation of motion. Okay? Then we get the following conservation equation. Says there were a couple of subtle points, so you may want to sort that out in your head. So, for instance, this equation is true when 5 solves equations of motion. But on the other hand, I said that I can consider field which is arbitrary in whose transformation. Okay, So, I mean, this much is therefore true regardless whether the phi in the work satisfies equation of motion or not. This much is just true, right? But then I can extract the particular information that also I'm not viewing this term as a surface term. I'm not viewing this term as a surface term, right? Why am I not doing it? Because this doesn't necessarily die at infinity. So I'm not viewing that way. Rather, I'm viewing like there's a divergence of something that I have to check every point in the board of the space and time. That's how I'm viewing this expression. Okay, so at this point in the space and time work, if we look at the configuration now satisfies equations of motion, then that thing must satisfy. So let me refine this expression because I said that the arbitrary transformation for infinitesimal transformation can be written as small parameter epsilon times the Wang-Bill transform. Likewise, remember what is the derivative of f? This is the consequence of actually varying action with respect to that symmetric transformation. So this f is going to be proportional to the epsilon 2, right? This is a result of doing epsilonic transformation. So I can write also f mu as something that is proportional and then whatever the rest f hat. I'm just using the notation. Okay, is the logic clear so far? So then if I plug back in, then in principle, this equation is epsilon times divergence of the rest, right? So therefore, I can get a covariance. Space, which diverges, which is the conservative. So what I've done is I just said that this is proportional to epsilon. This is also proportional to epsilon. I just designed my notation as stripping out the epsilon to the rest, plug back in. I say, oh, there's a conservation equation. Let's strip off this epsilon factor and the read of the rest, and I'm saying that is my current. So, so this is Noether hero. Okay, given an action, if there is continuous symmetry that leaves the action invariant in a sense that it satisfies this equation. Then for each, remember, for each transformation, if there's some notion of independent transformations, for each infinitesimal transformation, I have associated, conserved current. And this is called Noether's current. Okay, so that's the general statement. Now we're gonna do some checks for space-time symmetry. Any question?
You have distinguished between the when you obtain the EOM, you just vary the field, and here you're just doing the symmetric transformations, right?
That's right.
But when we obtain the EOM, so we also make the delta phi so that the point action does not change, right?
That's right.
So is there any meaning to distinguish between?
Good. So yes, there we consider arbitrary variation everywhere in the board, but something that actually dies off at infinity. Okay, there's a fine print if you want to go into that, but ask me. So that's it. So Berg, arbitrary variation, but then it dies off infinity. So this just drops out. Therefore, to demanding that action should be extreme point under arbitrary variation, which basically looking at the minimum point or extreme point of action, must come from the configuration where it solves this equation equal to 0. Now we say let's make a symmetric transformation that again leaves action invariant, but in such a way that now variation of the field at infinity may not die off. In fact, for arbitrary phi, if I just make a transformation, it will not be 0. So this term does not supposed to go away, right? So general, therefore, expression that basically say this statement is that this with the symmetric transformation, and then that minus of that thing, and divergence of that, right? This is two expressions. The that was general. Now you can try to learn extra information. Okay, that is mathematically true. Then you say, oh, if I just look at the configuration that not actually satisfies the equation of motion in the work, then there is a general property of the theory that it must have this quantity. The question is, who is that? What is the physical meaning of this guy? You might say, oh, why am I just looking at the field configuration that satisfies the equation of motion then? A, if you do that, you learn something more. That's good. B, in most of the physics processes, like in fact, every physical processes, you're going to anyway shoot into the field or particle, and then you look at the particle that comes out of that as satisfies the equation of motion, right? So if you imagine doing some physical processes, right? There's the incoming particle and outgoing particles that anyway solves all equations of motion, and you're asking whether this scattering amplitude is constrained by some property. And that obviously will constrain possible form of that thing, right? So this is how we make use of symmetry. Another question. Okay, let's move on. Good. So now, as the first now application or whatever a manifestation of that thing, let's look at the space-time translation. Okay, so x mu goes to, just so that I have the form that there's a small parameter epsilon that I can take it out. I'm gonna design my small transformation as some number epsilon times say e mu. Okay, I mean sometimes you could have called it like epsilon mu, which I used to do it before. Okay. But I'm just writing in such a way that there's a small parameter epsilon, which is number, and then direction of that small transformation. Okay? Which is I write it as E mu. Good. So if this is a symmetry, what does that mean? Well, action shouldn't change if I do make this transformation, right? So it shouldn't matter whether I use that coordinate system versus that coordinate system if something happening here. And that we should prove that thing. So then the first question is how many independent transformations we can talk about meaningfully. What's the answer? Looks like there's infinitely many different kinds of translations we can talk about, but mathematically, structurally, what's the number of independent translation? What is the complete basis of translation? 4, right? So there should be only 4 independent, right? The rest can be a linear superposition of this thing, right? So the answer therefore is 4. Good. And that is captured by the fact that we have these 4 independent factors in space time we can talk about. And then we say that, okay, for each of those symmetric transformations, there must be a conserved current, right? Okay, so what that means is that let's guess already. So just based on that fact, we can make an already useful guess. So I know that I want to have a for space-time vector conserved current for each of those guys. So that means that for each of those, I don't know, like row, let me just use the row notation, that somehow there's some structure in such a way it's just turning into space-time vector. So there should be something that does this thing, right? Even before computing anything. Let me say that again. Because the nature of this symmetry tells me that there should be 4 independent transformations. So I should expect 4 different kinds of current, right? And then that 4 independent symmetric transformation is parameterized by 4 independent direction of the translation. So I know that there should be current for each of them. So I expect already something that have this structure should pop up at some point. Okay? In fact, we will see that this is not a momentum tensor. So let's see. Now, if you find that or found that this is too abstract, let's make some contact with something that you already know. Now we're gonna analyze this, but let's make a quick contact. We say there is no middle current, which is conserved. Okay, let's write it out. So 0, I. And then you may recall that in your E&M class, you learned this, I don't know how you call it, like continuity equation. Is that how you call it? Okay. You learned that there's this equation. Right? Either fluid dynamics or I don't know, E&M or classical mechanics, whatever course you took. Right? You have seen it at least once. So rho is called the density. There, J called current. And the physics of this statement obviously is if you just look at what happened to the density, it changes only if there's either a flow out or flow in. Right? That's what this equation tells you. So there was something should be continuous. It's not like something just always pop out or just idle. Right? There's a continuity equation. Now, in this context, if you look at this, obviously this called this structure immediately, right? So for this reason, if you just compare these two, it makes sense to call that J0 now is a density, but density of 1 is going to be, in general, some charge density. It can be electric charge, it can be some other quantum number, it can be space-time quantum number, but some charge. It's called the charge density. And then Ji, obviously, is current. So in that sense, so now we understand there's this thing built in there. This particular equation captures local conservation. I will just explain what I mean by that. But even before that, let me just now use this and then define the charge first. Make a comparison. Now, charge density is their charge. And therefore, charge, you can compute it by integrating charge density over the space. Okay? Again, here, what I'm doing is that given a space and time, I'm just slicing out and looking at the spatial slice, and then I'm defining my quantum mechanics eventually. So if I have a charge density there, I'm just going to integrate over the volume of space to get the charge. That's what I'm doing here. So then, in terms of this, let's ask what this equation tells me. So if I do that, then first I get dt over dOq, because if I just integrate this guy over the space, and then I just commute the derivative, partial derivative with respect to time, and then integration, that's what I get. And then the other side, which is 0, so it's equal to minus and then this, which is divergence of the current. In case you lost, this is I'll just rewrite that equation. So then by Stokes theorem, this is equal to the surface or boundary of this spatial slice, and then unit vector as usual. And this current, as you will see, well, even before that, if we look at this, this is going to be a function of phi and then derivative of phi. Right? So it's a function of phi, but not variation of phi and derivative of phi, which dies off at infinity, as we demanded. So again, when I say that now, I'm not going to go into any subtle distinction between the two. I'm just going to consider always that, for instance, if you like, there is no boundary if I talk about S4, or maybe there's a boundary, but it's at infinity. So you just consider that everything dies of infinity. Okay. So we get another equation, which is induced from the first conservation equation. So that thing now is global conservation. It's local. So now let's quickly talk about this. Is this equivalent to that? Or is this more than that? Or that is more than that? You can ask that question, right? Which one has more information? I mean, this step shows that this should be more than that. Right? Because when you just average over something, you lose some information, right? But rather than looking at actual fluctuation here, if you just do the average, obviously you just get average quantity. So this is more than that. Now I call local versus global, for obvious reasons, because this equation you can ask to occur at every point in space and time, right? This conservation must obey every point in space and time. This one, you just check, given a time slice, you check next time slice, you just compare whether Q here is the same as Q here. Because the total Q should not change under the time evolution. Okay, so you just construct a single quantity over the entire space, and they just compare whether that doesn't change under the time evolution. So this you check every point in space and time. So obviously, this is way more information than just single equation. Okay. And this is, if you like, virtue or I don't know, a benefit of continuous transformation. Okay, continuous, there's notion of a little of fluctuations everywhere. So you can check this equation. But if you make discrete transformation, like the rotation by 30 degrees, you will lose notion of this equation. You only get this equation, for instance. Okay, but hopefully we'll see some of those examples. Okay, so now I'm going to come back to this space-time translation. With this understanding, we're going to analyze this part of the story. But if you have a question, ask.
Is there any reason to set variation of action to 0? I think it is sufficient to set it as constant.
Here? Okay. So the question was whether I always have to consider whether this is small or whether it is the important thing is this is constant. Was that the question?
아니요. 그 델타 S는 0으로 줬잖아요.
Yes.
시메트리 트랜스폼에서 델타 S는 0으로 줬는데,
Yes.
근데 그걸 그냥 컨스탄트로 두면 안 되나요? 다른 이유가 있는 건지.
Well, if S actually shift, right? If S actually shift, then partition function. So okay, we haven't introduced partition function or anything. So action shouldn't change in order for something to be a symmetry, right? And I said that okay. So eventually we're going to talk about partition function or generated functional. Then don't be panicked. I'm just going to write randomly. Okay, we're going to construct some quantity, something that looks like this, which is a different way of quantizing the theory. But if this shift, instead of being just invariant, you modify the partition function. But when you modify the partition function, you have to re-normalize what you mean by probability equal to 1, so everything changes. Just like in static math, okay? So you used to study like something like that, right? Or if you want to get fancier, maybe there's also density of say, whatever, right? All that. But suppose you made some operation in your system, all of a sudden energy shifts by itself. But then remember, the probability is defined by, in this, forget about that for a second, theta minus theta of I divided by Z. Right? That Z was the normalization of what you mean by probability. And then if you sum over entire thing, you should get 1. That's what I mean by quantum mechanics. But so there will be just a shift action by, in this case, action, in this case, energy, but they are very much related. By some constant, instead of being completely invariant, you have to change the sense of a normalization of the probability. This then, in principle, touch locality issue, causality issue, and so on and so forth. But if you had some particular thing in mind, why you thought like maybe action shifted by constant is okay, tell me. I can think about it.
그냥 여기서는 네, 그냥 파티션 펑션에 페이즈 텀이 조금 추가되는 느낌인 것 같은데 문제가 되는 건가요? 그게 노멀라이제이션에 문제가 되니까 그게 로컬리티나 그런 부분에 문제가 생길 수 있어요.
Yeah, that's the eventual issue. But I'm saying, if you modify what you meant by partition function already, if you shift by constant, okay, usually for those of you who already learned partition function or generating functional, you learn that okay, don't worry too much about overall function. Eventually, you're gonna divide by that thing and so on and so forth, right? But eventually, but we don't mean that. We never meant that you don't have to worry about the overall size. We just meant that we can always take care in a consistent way. But here we're checking what is the consistent thing, if we can even construct procedure for. I'm saying just shifting by some constant will impose a problem with that process. Okay, any other questions? Yes.
So it seems that you were saying that local conservation has more information than global conservation.
Yeah.
And it seems like the local, we can do anything, we can do anything with local. So do we even have to, what's so good about the location?
Well,
global ones?
Good. So usually, usually we encounter this first. Okay, because electric charge should be conserved. Okay, or in usual system, not usual system, but if there's every symmetry has this, but only the continuous symmetry has that. But so therefore, under the parity, if there is invariant parity, or if you have such a rotation by the finite, or if you have symmetry that reflect with respect to surface, that thing all comes with the well-defined notion of a charge, but those will not have current associated with them. So this is intrinsic to all symmetry. Again, but then for continuous symmetry, you have extra information, extra constraint, if you like.
Oh, thank you.
To get imposed. Yes.
In my understanding, in symmetry transformation, phi and phi does not have to decay out at infinity, right?
Yeah, variation of the phi doesn't need to decay out at infinity.
Then, in the global conservation,
Yeah.
you remove the gradient J. Yeah. When you say of that, you say that phi and gradient phi is decay out. But I'm confusing that phi and delta phi does not have to decay out in.
The variation of the phi as a symmetric transformation would not, in general, be zero, especially space-time infinity.
Then phi and gradient of phi is always decay out.
Yeah.
In your
At least if we only talk about this class of theories.
okay.
Okay. But I wrote a lot about this part of theories too. So what I'm saying, just think about this for a second. Okay. So then that's true statement. Another question? Yes.
I have a comment
Okay.
of his question. So I think what he wants to say is that if we add some constant to the action, then the equation of motion doesn't change because it is just mere constant.
Right.
So what if the variation due to change and delta has become constant doesn't change the equation of motion, so
Okay.
what does matter? But you said that it due to the change of constant and partition function and that thing, so I wonder you are thinking about some anomaly things for this discussion.
Yeah, it's also related to the anomaly because it pick up the sum phase under the symmetry transformation. It's all so right. I didn't want to say that. It's related to that. A second, also say even if it's not anomaly, so if you want some physical intuition about that, adding a constant to the action is the same as all of a sudden dropping some vacuum energy into the action. And then you might say, well, you told me that, don't worry about it. Yes, I said that. But then eventually you will worry about it. Then such a thing can never be actual well-defined notion of symmetry in the full-fledged level of field theory. Okay, so let's actually look at concrete examples and build up some intuition about it.
Then the choice of current is not important. I mean, we can choose because its definition looks like partial mu J mu equal to 0. So we can choose any J mu that satisfies the equation.
Very good. So since you raised that thing, let me just first discuss that first. Although I was gonna say after that, but I think it's good order. So okay, with that content, let me first explain related to the part of the discussion, and then you can ask me again if if you still have that question. So what I'm gonna show, hopefully using this space, is that why the definition of Q is unique. The definition of J is not unique. But then to the extent that it will always impose the same physical constraint. But there's ambiguity of some details of writing this expression. So let me just explain that again. So Q is unique, while J may not. So this is approach from the simple thought. So this is 0. That's what this is to satisfy, right? On the other hand, we know that this of A mu is always 0 for any such thing which is antisymmetric. Sorry. Mu, that's right. Yeah. Right? So if I take any antisymmetric tensor, obviously, if I take the derivative, which always familiar, it's 0. And this antisymmetric, symmetric, always 0. So I can make use of this. This is a mathematical fact, right? It's nothing to do with the physics for a second. So then I can modify what I meant by the current by saying, okay, let me just take the original I, which was derived in the concrete expression, and then I can orient this guy. Because then I can just take the derivative with respect to the mu, that's original guy, that's always 0. So it doesn't change anything. Also, like I said, this is just mathematical identity in a sense. So you will not modify the physics content, but what it can do, on the other hand, is that it can modify the detail of the property of the conserved current. Okay, so which I will introduce actually in the discussion of the momentum tensors. So anyway, for now, you just understand there's this much of ambiguity in writing explicit expression for the conserved current. Now let's see why the Q is still unique. Just look at that. So let's just look at the J equivalent and see whether that's same as the one in terms of J. That thing has therefore J of 0, and then I'm just gonna take the 0th component of that thing. That's I 0. So in principle, you have to sum entire nu, but 0 corresponds to 0 0 0. Well, A of 0 0 is 0 because how many times did I just say? A of 0 0 is 0 because that's antisymmetric, right? So then you see that this is total divergence. Once again, we are only talking about this theory where say there's no boundary, for instance. If you want to go a simple-minded way, that drops out, and so Q is the same as the Q that you constructed before. So the expression for Q, or even just Q, is unique or uniquely determined, but J has this ambiguity, or viewing this as a positive way, you have a freedom to add something if you want to see a particular property of J, which we will see momentarily by discussing the other one. Okay. Let's move on. So let's continue with this part of the discussion. Now we're going to talk about data translation. Okay, so let's do it. So let's take a scalar field. So under translation, scalar field. I mean, let's just take one scalar field. This transforms as oh, I'm doing the translation now. But obviously, this is that plus epsilon. What did I say? E. Right? So I just translated it. So then this is equal to, for infinitesimal epsilon, that's equal to, let's read it as a rho. So derivative epsilon E rho, derivative rho, phi of x. So I just expanded it to the first order in the parameter. What am I doing here? What am I doing here is that, remember, the current, the general expression for the current, let me just remind you, take the Lagrangian and take the derivative with respect to this. If you have multiple field, then put this guy, remember this was related to the just variation by stripping out epsilon vector. Let's subtract how the Lagrange transform. Remember, f was derivative of f epsilon. That thing was how the Lagrange. So basically, in order to construct the current, I just need to have how field transform and how Lagrange transform. Then I can just construct the current. That's what I'm doing. Okay. So first, I just check. So therefore, from this, you see that this without epsilon is d of 1 of x. So I have 1 known. So let's look at the change of the Lagrangian then. So Lagrangian says phi and the derivative is phi. First, it's gonna do phi and derivative, sorry, the variation of phi, which is epsilon times like okay. Then make the derivative with respect to derivative phi. And then how this gets transformed epsilon of e this is the original guy. Again, I just did this. Okay. So that thing is equal to epsilon, which is common and constant, times here's the plan. Epsilon this it is Lagrange. Okay, so let's take a look at it together to see if it makes sense to you. Okay, so if you have a function which has a more than one variable, and if you want to take the just derivative, which comes from the fact it is a function of x, with that shift, right? How do you do? First, you take the derivative with respect to the first argument, and then take the derivative first argument with respect to x. That's exactly what it does, right? With that shift. And then you take the derivative of this function with respect to the second, and then take the second one and do the differentiation with respect to x. That's exactly what this does with that shift. But this is overall just derivative of Lagrangian with that much of a shift. In other words, this is literally coming from the fact that just shift by epsilon e. And then just look at how this is transformed. Right, which is true because this is a function of that, you just shifted it, so you see how that happens. Okay. So remember, but I wanted to form this in the form where that looks like that thing, right? So I want to interpret it that way. So let's do it. So I can just change it, epsilon, derivative, then e. I can move around together, right? Like that or that. So then you just put down, and then you row Lagrange. Let's see how that works. So first of all, we are talking about the global. Okay, did I say ever? We are talking about the symmetry. When I say symmetry, I meant the transformation, which is space-time independent. In other words, here is the field phi, here is the field of phi, here's the field of phi. When I make the transformation, they transform exactly the same way everywhere, like that. Okay? It's not like I'm gonna do this, I'm gonna do that, I'm gonna do that. I'm not looking at that. So I'm looking at the transformation where this parameter, transformation parameter, is space-time independent. So everybody exactly do the same thing. Okay, that's what I'm saying. Such a transformation is called the Glover symmetric transformation. Glover means that it's the same everywhere. In the context of symmetry. Okay. So that's what I'm looking at. Therefore, first of all, these two are just constant choice, constant thing, meaning it doesn't depend on space and point. So it doesn't matter whether I can put it in or not, right? Second, I had a derivative with respect to rho, but I can just do it by contracting with the metric, right? So this I just rewrote exactly the same thing. So therefore, this is my f. Good. Okay, so therefore, now I can just write down the answer. my current, therefore, J of mu is equal to partial derivative of Lagrangian with respect to this. If you have a several field, there's gonna be that thing. If not, no. This one was what? Rho field, there were several, and then Fn, we determine. Sorry. No. Not this. Okay, I just literally plugged in. According to the So you see that you can rewrite it as if E of some rho pulled out, and then you can write the rest. And then remember we said, okay, because there are 4 independent space-time translations, I expect that to have current for each of those, so there should be something that achieves that, right? We talked about this. So from this, you see that here, this object, the square bracket, is nothing but therefore T rho mu, and this is known as canonical, as opposed to what, which I would say, energy momentum. And you know the at least physical meaning of that, right? So the energy momentum tensor is a conductor current as part of it for space-time translation. So my next thing I want to explain, well, canonical, but before that I want to explain energy momentum part first. Okay, why this interpretation in terms of energy and momentum at all? Okay, so let's first look at it first. So once you have current, then you know you can construct charge. So let's first look at that in order to understand the meaning of this thing. So as we talked about, there are 4 independent guys. So let's first look at the direction where I choose this to be timeline. So it's just point along the time direction. Okay. So then the associated current for that part is, well, if I choose this is the parenthesis completion. Let me just do it. Plan on it. So the Z0 associated with that thing is T00, right? Because the rest of the component dies out. The only thing that survives is the zero component. What I mean? So therefore, the check is what does this do? So let's actually check T00. And I have a definition here, so let's just write it down. So derivative of that thing with respect to phi dot, and then that thing is phi dot, probably phi dot, and then 0, 0, that's 1 Lagrangian. And we know that the partial derivative of Lagrangian with respect to phi dot, that's conjugate momenta in the phi dot minus Lagrangian, right? And you recognize this as a Hamiltonian density. So if I construct it therefore charge associated with that thing, which now it's going to be called H, right? As a space integration of this 0, part, which is this. So it's energy. So you see that what is the interpretation of this thing? This is the math. Now physics says that if I make time like translation or time translation, right? There's a conserved current along the time direction, which is this, which is energy, right? So time translation invariance means that energy is conserved. So that is energy part. This T mu has energy in it. What about the other one? So now I can take, this guy to be some direction of 0, E I. Let me just write this. Okay, so there's some space like vector EI. Or hat, if you like. So then the thing that I want to show is that whether it is a momentum, if I do that, and in that case, I want to show whether P of I0 takes interpretation in terms of momentum or not. But that's not exercise to do. So first of all, let's just write it out what that looks like. So TI0 is remember the second entry comes with a derivative. So I got, and then derivative of I minus G of I0 Lagrange. So that part is 0. So only this term survives. Here I just use notation, it doesn't matter, but the down derivative of phi is the same as u gradient. But here we have up I, which means that I have to raise it by metric, but spatial part of the metric has a minus sign in it. So this thing therefore is equal to U3x, that is the pi, that is therefore minus of gradient of it. Okay, so why is this momentum? Let me just demonstrate using a free scalar field for that. Okay, but this definition should be true in general. So for free scalar, again, just to demonstrate that this indeed give you momentum. Free scalar looks like this. Lorentz invariant measure, and then there is positive energy guy according to wave function interpretation, which is turned out to be wrong. So negative guy the negative energy. Okay. So now let's schematically show you why this should work out. This is time derivative of phi. So if you take the time derivative of this guy, what you do is that you're taking time derivative here, time derivative here. All right. The result of that thing is pulling out energy factor out, down. Okay. So you have to follow my thing, otherwise you will lose. All right. Do the time derivative, pulling out energy. That will cancel out this. Okay. When you do the spatial derivative on it, instead you're pulling out momentum down. And then there are, because there are two fields and the one space integration, there are two momentum integration, there's a one spatial integration. Spatial integration will give you one delta function, blah, blah. So I mean that, do it. So anyway, I show you that this will cancel 1 over 2e. This will pull down 1 over momentum, but there are two momentum integration. At the end of the day, what you should get is P and then have A. Now instead of this alpha, I will also explain that. This is what you get. Okay? You might say, oh, I'm confused, you might say, because I had a two momentum integration, I had the two factors of 1 over 2e. I understand that one time derivative cancels one of the 1 over e. What about the other 1 over e? So that is related to the normalization. Remember, alpha squared is the same as a squared times 2e. So that cancels another factor anyway. Okay? And that spatial derivative pulling out the momentum factor. Anyway, so you can just work it out exactly, but I'm just telling you that it works out that way. So what is this thing? Okay, we have seen this, so I can use commutation relation. Oh, not even actually to this. This is still double here. Okay. So we talked about this. Okay, there's this zero, there's UV, IR divergences, or you can just impose normal ordering if you want to avoid that and so on. We talked about that. Anyway, the point is that yes, the TI0 component integrated over the space indeed it turns into total momentum. This is sum over the number of particles at each of the momentum P with the momentum measure there. So it's the total momentum. Indeed, it is that. Okay. So the summary is that we have gone through the exercise that given an arbitrary Lagrangian, we consider space-time translation. We got this generic expression that works for everything, and the name is just fine by just looking at these two quick exercises. It is an energy, momentum, and tensor. It is not a vector. It is energy, momentum, tensor. Now, what about the canonical part? So I just need to go why this has its own name. Okay, that's the last thing I want to do. So I'm gonna make use of this space. This is, I think, enough. Say that. So canonical versus what? So the thing comes with canonical versus probably. You know what? I forgot the spelling. Bellifante. Who remembers the spelling? So there are at least three different kinds of energy momentum tensor. We just saw canonical energy momentum tensor. There's Bellifante Rosenfeld energy momentum tensor. There's this another one constructed by three people, Callan, Coleman, and Jackie. I'm not going to go into the detail, but I can at least explain to you why you might expect that there should be such a thing at all. Okay. So first of all, remember that given a J, there's ambiguity about the J, but not on the Q. Then I can always add some anti-symmetric tensor to that. And anti-symmetry in the sense that I introduce auxiliary extra thing, but the mu is the one that is about the conservation part, right? So now here we say, in the case of a space translation, I have this guy. So let's write down the equation associated with this expression. So I can write it as original d mu. Now I want to add something. So this, remember, is about the which space-time translation is all about. So I'm not going to touch that. There's this guy, which is about the conservation part. So I'm not going to touch this, but I'm going to have something that is anti-symmetric in this group. That called this structure. Oh, right? So this is the formal freedom or ambiguity that you can add to what I constructed there. For what? So energy momentum tensor can be symmetric in those indices. Okay? Can be, where is it? Symmetric in those indices. But oftentimes, sometimes at least, the canonical one, if you just compute it out of the box like that, will not be symmetric in those indices. Because if you look at this, this is symmetric. But a priori, you don't have a reason that this to be symmetric, right? So if you are given a specific Lagrangian computed, it may not come out to be symmetric. Especially when we talk about the spin field rather than scalar, we can talk about fermion vector and so on and so forth. Most of the time, it will come out to be non-symmetric. But then what you can show, according to these two person, is that you can make use of this freedom, for instance, to achieve. So let me just give it a name, theta of rho. So you can always achieve that it is actually symmetric. So that is the Bellifante Rosenfeld tensor. Okay. Now, there is a theory that has more than just, concrete transformation. It is also invariant under scaling of the space and time. It's called a scale transformation. Okay, you can just make it smaller, bigger, but theory doesn't change at all. Okay, for those scale invariant theory, one can show that energy momentum tensor needs to be traceless. But again, either this nor this, if you just compute it out of the box, may not satisfy the equality. So the short mathematical question is, what is the property that such a symmetry must satisfy? One can show that scale invariance always lead to traceless energy momentum tensor. But neither you may be confused, right? You just look at it. But again, there's this ambiguity of freedom. You can design to add a proper terms like this to achieve this property. This is the Coleman. Okay, anyways, there's this freedom you can make use of to achieve some of the nice properties. Okay, even though it may be opaque if it's just not even have this version. Okay, so that's the translation part. Let's move on to the Lorentz. What the question? Yes.
Could you give me some hints how to derive traceless?
Yes.
Traceless.
Oh.
I heard of American development tensor, but I never heard current Coleman.
Yeah, I also need to remind that this business is a serious business, as you may know. Right. There's this business where the scale invariance implies control invariance. You have heard of that. And it is one of the central business there. I don't recall immediately the actual derivation, but I have to look at the paper if that's what you're asking for.
I just want to hear some hints how to derive.
Well, then basically I'm telling you how to construct that thing. So that part I forgot. It's rather technical. You have to play with the tensors and make sure that property. But I think there's a clear systematic. If I think I remember there's a clear systematic. Basically, just demand what property A needs to satisfy in order for that to be true. We already can start writing that, right? Just look at the trace part, and that means that thing is zero. You can start deriving the property. And also, when you do that, it's not like you only impose that without imposing it. So you also want to impose that too. So then you get that list of multiple conditions on that, and then you just mathematically see what construction can be done. So that's sort of logic, but I just don't remember really the actual sense. Any other question? Okay. So let me spend like 5 more minutes or so to touch on the Lorentz part that we are in the phase that I wanted to. This will come out again, so let's skip it. So let's talk about non-Lorentz. Is X mu goes to mu. Remember this. Okay, and Lorentz was defined in such a way that if I had a metric, if I do transformation on it, it doesn't change metric. So that was the definition of the Lorentz transformation. It's isometry. And for infinitesimal transformation, you can write it as F1, which is delta, plus little small parameter, which let me write it as this. Once again, just like the translation, I introduce a small parameter because I'm looking at the infinitesimal transformation, and then I'm just keeping track of tensorial structure by this guy. Okay? And then if you plug back in here, you learn that this, I'm just reviewing this. If you plug back in, you should learn that this is antisymmetric tensor. We talked about that. So 4x4 antisymmetric, there should be 6 independent transformations, and 3 of them are rotation. And then 3, which is flux. We talked about this. So rotation is mixing different space indices. Boost is mixing one space indices. So it's completely parallel structure. Okay. Now, for us, in order to consider conserved current, what do we have to do? Well, I need to know once again, what is this? And then, what is this, which is original energy. So basically, I need to know this, and then I can write down the conserved current. Right? It's the same exercise. Okay, so this will appear again. So remember, Lagrangian, derivative, this will appear again. Okay, it's going away. So let's work out this. So I'm working on the scalar. So if we look back, the way scalar transform under the Lorentz transformation in the quantum Hilbert space is this way, which is equal to phi of inverse. So I told you like that, and you modify the background, it goes the other way around. Look back or not, it looks like. So for now, you can just phi. So let's work it out. This is basically this is how what is this? What you call transform the field. So let's work this out. If I write schematically, lambda is 1 plus epsilon omega. You can put all the indices if you want. Inverse is 1 minus epsilon omega. Right? At order epsilon. Right? If you just product of 2, 1 plus something, you minus that thing, and then order epsilon squared, which I draw. Okay? So that is the proper definition of inverse. Right? If you product of 2, you get 1. At order epsilon. Okay, so then phi of this is equal to phi of x minus epsilon omega x. So if you want the index, this means for x rho, this is scalar, rho nu x nu. That's what I mean. I can put the Lorentz indices as well. So this is a small what? This is a small translation. But then translation parameter is not anymore just complete constant, but it has x in it. Right? So, but you know that the generator, okay, I shouldn't use the generator yet. The noise current for translation was energy momentum tensor, we just saw. But therefore, the noise current for this guy will be some version of an energy momentum tensor, but notice not the fact that translation is with the size of x itself. Right? So if this is a zero of the coordinate system, here translate a small, but there translate more, there translate more proportional to the x. That's exactly what a rotation looks like. Okay? So let's expand that out. That's why you will see, at least hopefully, 21. So that the noise current will have energy momentum tensor together with x in it. Expand this out. Phi of x, epsilon, omega, rho, nu, x nu, derivative of phi. Right? The same way we talked about. And then the way Lagrangian transform is again the same. Just like view Lagrangian as a function of x. Now basically you're looking at just like you had a field, and the field has the argument of this form. Lagrangian will have the exact same argument as before. Okay? So therefore Lagrangian will transform just like this is how including minus sign. This is how it will transform. Lagrangian must transform the exact same way. So it should be minus epsilon omega rho nu x nu derivative of Lagrangian. Okay, I almost ready to write down the current, but I'm not going to. Hopefully you get super curious. Sorry. And then I will write this down next time, so that you can come back. So next week we talked about, right? there is no lecture on Monday because you don't see, you want to see me, and then Wednesday I don't want to see you, so there's no good. Okay, we'll come back in 2 weeks. Okay, you guys have a great Thanksgiving. Enjoy. Don't eat too much, but enough. And I'll see you with some game. Okay. Good.